Electromagnetic theory is the study of electric and magnetic fields, how they arise from charges and currents, how they interact with matter, and how they propagate through space as electromagnetic waves. It is one of the most fundamental branches of physics and engineering. In this series, we will build the theory from the ground up, starting with the mathematical tools we need. Let's start with a visual. Here you see the electric field produced by a single positive charge. The field lines radiate outward in every direction. This is a vector field, meaning at every point in space, the field has both a magnitude and a direction. Now look at a magnetic field. These field lines form closed loops threading through this solenoid. Understanding these fields, how to calculate them, how they behave, that is the goal of electromagnetic theory. Why should we study this? Because electromagnetic theory is the foundation of almost all modern technology. Every wireless signal, Wi-Fi, 5G, Bluetooth, is an electromagnetic wave. Medical imaging techniques like MRI rely on magnetic fields. Power generation and transmission use electromagnetic induction. Radar, GPS navigation, fiber optics, antenna design, semiconductor physics, all of these are direct applications of the theory we will learn in this series. Before we dive into fields, let's clarify two fundamental concepts, scalar and vector fields. A scalar field assigns a single number to every point in space. For example, temperature. At each location there is one value, 25 degrees, 30 degrees. A vector field assigns both a magnitude and a direction to every point. The electric field is a perfect example. At each point, we can ask, how strong is it and which direction does it point? This distinction between scalar and vector is essential. Everything in electromagnetic theory builds on it. In Cartesian coordinates, we define three unit vectors, Ex, Ey, and Ez. Each has a magnitude of exactly 1 and points along its respective axis. Any point P in space can be described by the position vector r, which is the sum of its components, x times Ex plus y times Ey plus z times Ez. This position vector r points from the origin to the point P, and its magnitude gives us the distance from the origin. Now here is a key insight. Not every problem is best solved in Cartesian coordinates. When we have cylindrical symmetry, like a wire or a solenoid, we use cylindrical coordinates with rho, phi, and z. When we have spherical symmetry, like a point charge, we use spherical coordinates with r, theta, and phi. In the next few lessons, we will master each of these coordinate systems and learn how to express lengths, surfaces, and volumes in each one. Let's recap. Electromagnetic theory studies electric and magnetic fields and their interactions. We distinguish between scalar fields, which have only magnitude, and vector fields, which have both magnitude and direction. We will work in three coordinate systems, Cartesian, cylindrical, and spherical, each suited to different symmetries. In the next lesson, we will dive deep into the Cartesian coordinate system.